Welcome to this video on dynamic programming. Dynamic programming is an algorithmic technique that allows us to solve problems that span multiple periods. The process of dynamic programming recursively breaks down a complex problem into simpler subproblems. Using one key theorem, we know that the optimal solution to the overall problem is comprised of the solutions to the subproblems. Why do we need dynamic programming? The key difference in a dynamic programming problem is the way the input variable affects the problem across multiple periods. Specifically, the input variable not only changes the objective function in the current period, but also the constraints for future periods. That is an interesting form of optimization that we have yet to encounter. Alright, an example of this is that if you're maximizing utility across your lifetime, you often choose how much of your money to spend in each period. But the amount of money that you spend today affects your savings, and that impacts the amount of money you're able to spend in the future. So in this case, your input variable or your control variable is how much you spend on consumption today. And clearly you're constrained to being able to spend at most ST your savings in period T, and your savings tomorrow depend on consumption today. And thus we encounter a new type of problem that can be solved using dynamic programming. So if you were to think about how you'd optimize that, you can't just maximize your utility of consumption today based on your consumption today, because that will leave you with no money tomorrow. You need to factor in some money for those next few periods. And if you tried to make one huge objective function, it would be intractable. And that's why we use dynamic programming to solve these problems. Okay, so let's look at the notation for this. Often our dynamic programming looks something like this. This is a discrete time dynamic programming problem. You're given a maximization of an objective function that is this entire thing here. And here it's summing in discrete time from time equals 0 to time equal t based on your objective function for each time period. Notice that your objective function within a time period can depend upon t, so your utility function can change across time. And it's being impacted by your state variable and your control variable. Okay, your state variable for tomorrow is dependent on some function of your state variable today and your control variable today. And yeah, the idea is that the variables we can control are the control variables u. They're impacting our state variables xt plus 1 that will essentially be our constraints. And collectively our objective function across many smaller periods is being impacted, and the objective function, the overall thing, is this entire sum that we're trying to maximize. So just to summarize that, ut is the control variable, u is the control region, this capital U. That's saying that our control variables must come from this control region. And if we're looking at savings and consumption, the control region would be a percentage from 0 to 1. And that is how much you can spend of your savings. So you could spend 100% of your savings today if you want, or you could spend nothing, or anywhere in between. XT is the state of the system, so that would represent your wealth in any given period. And of course, your wealth tomorrow depends on your wealth today, how much you didn't spend of it. And then you can also include interest in this scenario. So you can see that every time you start in a period, you have this much money to spend. And the amount of money you can spend in the next period is dependent upon what you do with it. And that's, in essence, why we're using dynamic programming, because we need to optimize our lifetime utility very carefully in this context. Okay, so we can usually refer to this as, this is the with a strike through objective function at time t, because the entire objective function is the whole sum, but it's the sum of smaller objective functions. Kind of weird notation to talk about, but the objective function is the entire thing. And yeah, just pay attention to the fact that this can change based on your time period. There's no reason that your utility for today has to be determined in the exact same way as your utility the next day. And so we can account for the fact that your preferences can change by having your objective function within any time period changing if it wants to. Okay, and then yeah, the objective function is the entire sum. Okay, so what we're looking for, what we're looking for in these questions is ultimately the optimal control, which is your choice UT across your life that will optimize your utility across your entire life. And that will come with it the optimal pair, which combines your control variable with your state variables. And these are optimized amongst your admissible sequence pairs, which are all of the possible variables, control and state variables you can have together. So the idea is that you can have a sequence pair that is admissible if the combination makes sense, if it's feasible, if you could actually go ahead and do it. Like you can't spend U equal to 1, so 100% of your money every single day, and have XT be $1 million every day for the rest of your life. That wouldn't make sense, because if you spent all of your money in time period 1, you're going to have nothing left the next period. So that doesn't qualify as an admissible sequence pair. So the first, I suppose, filter is on sequence pairs that make sense, that are possible, and that you can achieve given your control variable choices and your state variables that are impacted by that. And then out of all of those possible pairs you have, what is the best one, the optimal pair that provides you the most utility, or more broadly maximizes your objective function? Yeah, that's I suppose the goal of dynamic programming, is to determine that. Okay, so we solve dynamic programming. Excuse the green mess. It says, how do we solve dynamic programming problem? Yeah. We solve dynamic programming problems by using value functions, the fundamental equations of dynamic programming, and backwards induction. And together, this process is dynamic programming. That's what it is. It's that algorithmic technique. And so I'll go through what these are and then apply them with an example. Okay, let's look at value functions first. So value functions will play an important role in our solution approach. So we need to understand what they are to use them properly. A value function is a way of maximizing your utility or your objective function, starting specifically at point S and going to the rest of time. That's our goal. So we're truncating the problem at time equals S to the end, and that will form our value function from that point onwards. So Js of x is equal to the maximum thing here based on our control variables from the point S onwards. Okay, and then our constraints are as usual here. So an intuitive example, if we were maximizing our utility across your life and you knew that you were going to finish your life at 83, then J20 would be the maximum utility that you can acquire from the year 20 all the way through to the end. Okay, and the reason why this is useful is that we can then start to break down our problem into smaller subproblems and solve them. Okay, and the way that we practically do that is by using the fundamental equations of dynamic programming. And that is that the value function is equal to the max control variable here of your smaller objective function at time S plus Js plus 1. That's it. So the idea is that we can split up our value functions here, where J20 is equal to max F19 max F20 plus J21. That's essentially what that is saying. So in a very loose notation, that's what it's saying. Our value function for time period 20 is equal to our value function for 21 plus your optimal decision at specifically time 20. And that makes a lot of sense, because if J20 is the maximum utility for the rest of your life, then that is equivalent to the rest of utility maximized from 21 to the end, plus individually maximizing it on the 20th period. They will be equivalent. And this connection to the value function and then what it is today versus for the rest of your life, that allows us to actually practically solve things by working backwards. So the solutions to these max problems provide the optimal pairs for the overall problem. Okay, so let's put that together to solve an example using this. Okay, so find the optimal pair for this problem here. We've got u0, u1, u2, which are real numbers, and we have an objective function that is summing from 0 to 2, 1 minus xt squared minus 2ut squared. And our state variable xt plus 1 is equal to xt minus ut for t equals 0 and 1. And then x0 is just starting at 5. Okay, so that's our goal, is to maximize this and find the optimal pairs to maximize it. Okay, so we solved this by using backwards induction and the fundamental equations of dynamic programming. In period 2, so our final period, this is something I'm not sure if I highlighted before. Our final period, jt, so this is the final period there, t, is just equal to the maximum of your small objective function at time t. So there's nothing coming after that time period. So the optimal utility is going to be determined by your decision solely on that period. Think of it like this. If you were to start the year 83, this one here, you're going to die once that year is finished, and your value function at that year is just optimizing your utility for the rest of your life, which is one period, which is just simply optimizing your objective function based on your choice variable u and how you start that final year. So going back to our problem, we're now maximizing here f2, x2, u2. In this case, the time period does not affect our f function. So we just plug in x2 and u2. And plugging that into this simply gives us this. And the idea is that we have no control over how we started this final period. We just start with x2. And what we're trying to figure out is how should we respond to that by choosing u2 optimally. So we want to maximize this. Okay, and the quick answer to that is if you want to maximize this whole thing, you want to set u equal to 0, because when u is 0, then you will not subtract anything from this u2 squared. And that gives us here u2 equal to 0 as our optimal. And this is just verifying using simple one variable optimization techniques based on the first order condition being 0 and our second order condition showing that it's a max, that this is our optimal control variable for this period. And altogether, that tells us that our value function at period 2 is simply equal to this, and that our optimal control variable in response to x2 is just 0. So think of it like this. If you start the final period, your value from the final period onwards is just going to be equal to this optimally, and your best decision in response to x2 is to pick 0. So actually it doesn't depend how you start the final period, you just pick x2 equal to 0. Okay, and now we work backwards. So we go to period 1, and period 1, using our fundamental equations of dynamic programming, is maximizing our smaller objective function, our f function evaluated at time 1 plus j2, and then j2 is going to be based off x2, and x2 is determined by this. So xt plus 1 is equal to xt minus u2. So our j2 function here, which is j2 of x2, is going to be equal to this, as that is what determines x2. And now we've converted the whole problem into something that is based off one variable that we have choice over, which is u1. Okay, so what is the j2 function? We know the j2 function is this because we derived it before. So we want to plug in j2 of x2 as j2 of x1 minus u1 and plug that into this. So moving forwards, we can plug in exactly what j2 is and evaluate it at x1 minus u1. And then we can expand that out and simplify, and we get down to this. And now again, we have a one variable problem where you have control over x1. So you have control over u1, and you just start the period with x1 as your resource with no control over that. And the idea is that we're going to find the best u1 to pick in response to how you started it with x1. So we optimize this by differentiating it with respect to u1 and finding the maximum. So differentiating this with respect to u1 gives us this. And our first order condition, which is setting that equal to 0, is solved by giving this. And then second order condition confirms that it's a global max because it's negative. And therefore, we know that this is our optimal control variable based on our state variable x1. And plugging that into the equation above gives us our j function here. And rearranging that all down is ultimately broken down into this. So now we know that we want to pick this as our u1 that is optimal based on however we start this period. If we start it with x1, we will optimize our lifetime utility from that day onwards by choosing it in this way. And then our remaining lifetime utility will be equal to this. Okay, and then we go again to period 0. So period 0, using our fundamental equations of dynamic programming, is simply our f function evaluated at 0 plus our value function plugged in with x1, which is determined by this rule, and then maximizing it with respect to u. Okay, so we can go through this. If we plug in our x0 minus u0 into this, we're plugging it in right here. And so that gives us this here. And then once we're into this, we just need to expand and simplify. So you can have a look through that algebraically, but you ultimately get this as your answer. And once you're here, it's the same thing. It's working out the optimal u given the fact that you're stuck with x0. And if you do the single variable calculus, you get this. Make sure again that you check the second order condition so you don't accidentally minimize this by mistake. Okay, and once you work out your optimal optimal u0 in response to x0, you can plug it back into what is above and work out your value function at time 0. And doing all of the simplification mathematically will give us this. Okay, we're almost done. Almost done. Now that we've gone from the start to finish, we have our rules for the optimal choices at every time period. So when you start time 0 with x0, you should choose this for u0. That's our optimal decision making. And then we know from before, if I can just grab it again, u1, that's our optimal decision based off how you started with x1. And then u2, that's our optimal decision based off how you started with x2. And then we also know that our our state variable is going to change according to this rule here. So we can put that all together to wrap up our answer and find the optimal pair. So we know that x0 is equal to 5 at the start, and that our rule is governed by this. So when time is 0, x0 is 5, and we want to work out u0 in response to 5, which, using the rules from before, which I've just rewritten here, that gives us 25 and 11. Okay, then x1, which is equal to x0 minus u0, we know what those are now. We just take 5 minus 25 and 11, and that gives us this. Then we plug that into our rule for working out what u1 should be in response to x1, which gives us this. And then time is equal to 2. We work out what x2 is based on the difference of these. And then we already know that you set u2 equal to 0 no matter what. And summarizing that all together gives us our optimal pair, which is our sequence here given by our state variables and our control variables that are optimal. And this will give us the solution to the problem that will maximize this here based on our choice of u as a real number. All right, I know that's a lot of information, but this is the end of the video on dynamic programming that we've been looking at in discrete time. I hope you found it helpful and that you learned a lot along the way. Thanks for listening, and I'll see you next time.